theoretical yield, limiting reagent. And so we ended with this problem, right, where you assume, let me go all the way back here, right? When you have a problem like this, you assume each reactant is limiting reactant, and then you convert each reactant into moles of the product that you're looking at. So in this case, it was nitrogen gas. You see which one makes less, and that's your limiting reactant. That determines what's going to make the amount of product you're going to have from this chemical reaction. So then you convert that amount of limiting reactant product, right, that you get into grams using the molar mass. And so these questions, so we have there's a couple other questions that you can go through in the notes, and they kind of have a step-by-step breakdown to kind of help you guide along the problem. These are all going to be related to eventually percent yield problems, right? So limiting reactant is kind of just doing like 2 mass to mole calculations in one problem, right? It just adds an extra step or an extra problem to a singular problem. So when we're doing the percent yield, basically this is comparing our experimental results and our theoretical results, right? So if we mix 2 things together, using stoichiometry, we have an idea, okay, based off the stoichiometry of this chemical reaction, I know exactly how much product I should make based off of which one is the limiting reactant, right? But in reality, things are never 100% efficient. You're not going to create 100% of the product that you think you're going to create. And so what we're going to do is we're going to look for the actual yield and compare that to our theoretical yield, right? And so you need an actual experimental data to be able to do this. So you actually do this in the lab. And then you need to understand the relationship between the actual and the theoretical yield. And so really it's just taking the actual yield over the theoretical yield and multiplying that by 100%. That's because this is from our balanced chemical equation. And we get this by assuming that our reaction is 100% efficient, right? That every limiting reactant that we put in there is going to be converted to product, right? Assuming it is 100% efficient. So this is the reason it's called the theoretical yield, is because this is theoretically the maximum amount that we could make, just based off the numbers, right? If we just crunch the numbers, this is the maximum amount of our product that we can make. Our actual yield, this comes from experiment, right? So this is, okay, you guys go in the lab. Some of you, you're trying to remake some copper in your solutions, right? So you dissolved some copper last week. You put it through a number of redox reactions, right? And you should have had copper in the end. Theoretically, you should end up with the same amount of copper that you started with, right? So did anyone end up with the same amount of copper that they started with? That's right, because our scales weren't sensitive, right? But yeah, you were close enough within a decimal place, right, to the actual amount of copper that you started with. But for the vast majority of us, and myself included, if I were to do the experiment, we probably wouldn't end up with the same amount that we started with, right? So it's the same thing for any reaction. We have the theoretical maximum that we can make, but most likely you're not going to get 100% efficiency because there might be some side reactions that happens. Maybe one of your reactants gets oxidized and it doesn't participate in the reaction. It's never going to be 100% efficient. So the actual yield is always going to be less than the theoretical yield. Actual yield is less than the theoretical yield. Always. And that means that this ratio right here is going to be between 0 and 1, right? That's the maximum that we can have. Some of you guys have seen yields over 100%, I believe, in the magnesium oxide lab. Some of you saw that. Or in the copper lab, you might have seen that. And that's because other times maybe you didn't dry off all your water, right? So your water's adding to the mass, it's adding to what you would expect to just be your product, right? So if you ever have a percent yield over 100%, that's impossible physically. It means that there's something else going wrong with your experiment, right? But in terms of especially when we're just doing calculations and lecture and theoretical calculations, these are always going to be in between 0 and 1.
What does it say
from the balanced. Let me rewrite that. Yeah, even the software thought that didn't look like anything because it put the red dots under there. Balanced, right? So from the balanced chemical equation, and again, we have done a lot of balancing because your dry lab a couple weeks ago was in balancing chemical equations, so you have had a lot of practice doing that. You always want to be dealing with a balanced chemical equation. If it's not balanced, it doesn't make any sense. You can't do these number-to-number conversions. Okay. So for example, are there any questions on this actually before I go into an example? Right? Any questions here? Maybe how it's related to a lab that we've done, or if any of these ideas are confusing. No? Okay. And then actually I just want to add, this is from calculating the limiting reactant. And this also requires, you have to know beforehand what the actual reaction is, right? You can't, if you don't know the reaction, you can't calculate the theoretical yield. Okay. So for example, if you have an experiment forming ethanol, the theoretical yield is 50.5 grams and the actual yield is 48.6 or 46.8 grams, right? This is, the actual is always going to be less than the theoretical because in nature things aren't really 100% efficient ever. So if we see the ratio, 46 divided by 50, that's a smaller number divided by a large number, that's going to be less than 1, right? And so here, this is a pretty good yield, right? Generally, if you're looking at industrial chemistry for scaling reactions and stuff, you usually want to get above 95% yield for things, right? So this is still would be considered not really sufficient for a industrial setting, but if we had this in lab, that'd be great, right? If you guys all got 90% of your copper back, we'd all be amazing chemists, right? But we didn't. But you guys are still amazing chemists, amazing chemists in training. Right, so if we're already given the values, it's a relatively simple calculation, right? We just plug it into our relationship, right? We just identify what is the actual, what is the theoretical yield, and then you plug that in. But we're probably not going to see it like that most often, right? Because this is just a way that we can layer other problems that we're asking already, right? If we have limiting reactant, these mass-to-mass calculations, chemical quantities and all of that, this is really, you can add all of those into one singular question that's saying, okay, you have this reaction, you mix these two things together, what is the percent yield if you had this as your actual yield, right? That's a very short word question, but requires knowledge of the different type of conversions you need, how to find the limiting reactant to determine how much you'll actually make, and then plugging that into our percent yield equation. Right, so let's say we had an example like this. Silicon carbide can be formed from the following reaction, right? So we just have to make sure that it's balanced. When 125 grams of sand is processed, 68.4 grams of silicon carbide is produced. What is the percent yield in this reaction, right? So we're given, all of a sudden this question that, this idea that seemed relatively straightforward when it's just given to us in a simple relationship is a lot more complicated when we look at it in an actual physical context, right? So the first thing we want to do whenever we're given a chemical reaction, in my class, I'll most likely always tell you to balance it if it needs to be balanced, but in general, for standardized tests, it will not tell you, bless you, it will not tell you if you need to balance the equation, right? So we'll just check to make sure this is balanced. And so we can check to make sure that it's balanced by counting all the different elements on either side. We have silicon, oxygen, and carbon atoms, right? So we have silicon, oxygen, and carbon atoms, and we have them both on the reactant and both on the product side, right? So on the reactant side, how many silicon atoms do we have? 1. How many oxygens do we have? 2. And how many carbon atoms? 3. All right. What about on the product side? How many silicon atoms do we have? 1. How many oxygen atoms do we have? 2, right? Because we have 2 carbon monoxide molecules and each one has 1. So that's a total of 2. And how many carbon atoms do we have? 3 because we have 1 here and then 2 carbon atoms from 2 carbon monoxide molecules, right? So it's an easy spot to get mixed up. If the element is in multiple molecules, you have to add up each element from each of the different molecules on that side of the reaction, right? So we have 3. So our reaction is balanced. We have the same number of atoms on each side of the reaction. So at least we don't have to balance that, right? If it was a makeup quiz or an exam question, then maybe you would probably have to balance this first, right? And then use that to go through the rest of the problem. All right, so we have the reaction balanced at this point. The next question is asking, when you have 125 grams of sand that are processed, right? So this is our sand, right? This is just silicon dioxide is our sand. It says 68.4 of silicon carbide is produced. Right, so that's saying that's the actual amount that you received, right? So in all of the topics that we've talked about, unit conversions, theoretical percent yield, and limiting reactant, what is that quantity, 68.4? Like, how would you label that quantity in this problem? Right, so what is this right here? How are we going to use this value? And then also think about how are we going to use this value? What is the value highlighted in blue there? Okay. It'll be the numerator for our percent yield, which is our actual yield, right? This is the amount of sand that's actually been produced, right? In grams, right? So, it's the grams are missing, you're right. Right, this is supposed to be grams, right? So that's just missing from here. This is our actual yield for this reaction here, right? We started with 125 grams of sand. We're saying we measured 68.4 grams of silicon carbide. That's what we actually measured, right? So then what is the quantity highlighted in red? What is that? How are we going to use that? Say it again. We're going to use that to find the theoretical yield, right? Because this is the amount of reactant that we're starting with, right? This is our amount of reactant starting with. In this one, we're not actually going to have to calculate the limiting reactant. It's not listed explicitly in this problem, but it should be assume excess carbon here. So the reason we assume excess carbon, it doesn't give us an amount of carbon that we're starting with. It's assuming that all of the sand is being converted into silicon carbide, right? And so that means that this is going to be used to calculate the theoretical yield, right? So this is used to calculate theoretical, and sorry, I'll try not to write it below, theoretical yield. Okay, am I good to go on? All right. All right, so we're just trying to identify right now what's given to us in the problem and what we can use to solve for the percent yield. Say that, what? Starting with. Yeah, so that's just my abbreviation. I don't know, I could have just... Yeah, because we're already given the actual yield, right? To get the percent yield, we know because it's asking for what is the percent yield, right? That means that because it's asking for this, that we need to find the theoretical yield. Actual yield is given to us, percent yield we need to find. Okay. Are we good to go on? Any objections? All right, so calculating the theoretical yield. So we know that we're starting with 125 grams of SiO2. To calculate the theoretical yield, what do I need to calculate? What does this need to be converted to? Right, what is the thing we're actually looking for here? What compound? SiC, silicon carbide, right? And what do we need for silicon carbide? All right, what units of silicon carbide do we need? We need grams, right? Because our theoretical yield, or our percent yield, is going to be the grams, our actual yield, the grams that was given to us, over the grams of our theoretical max that we can make, right? So we need the grams of silicon carbide. You could do the percent yield in moles if you wanted to. No matter what, you're going to have to do an extra conversion at the end. So grams or moles, it'll give you the same answer. It's just whichever one is going to be easier. So we're going to go all the way to grams just because it's practice, right? So this is going to be a grams to grams calculation. So how many steps are there going to be when we go from SiO2, grams of SiO2? What do we need to go to first? Moles of SiO2, right? Because we always need to go to moles to convert from one compound to the next. And then that's going to be converted into what? Moles of silicon carbide, right? Once we're in the universe of moles, we can go between moles of different compounds, and then that gets converted to grams of silicon carbide. And that's going to be our theoretical yield. And what do we use to go from grams of silicon dioxide or sand to moles of sand? All right, in the first step, what chemical quantity we use? The molar mass, right? The molar mass of SiO2. Then to go from moles of sand to moles of silicon carbide, what do we use? The molar ratio. And then to go from moles of silicon carbide to grams of silicon carbide, what do we use? Molar mass of what? Silicon carbide, right? So those are our steps that we're going to do. So we're starting from 125 grams SiO2. We're going to use the molar mass. And so what is the molar mass of silicon dioxide? No one calculating. I guess I'll calculate it. Of SiO2. 60.808 grams of SiO2 per 1 mole SiO2. Why do we want to use the inverse of the molar mass here? Because we need to cancel out the units of grams, right? When we're going into units of moles, yeah, same thing. That's cancel out, right? That can be our hand symbol for your cancel out. And we end with units of moles of SiO2, right? Which is where we want to be after our first step. Then we use the molar ratio. And where do we get the molar ratio from? The balanced chemical equation, which we know this is balanced. And what is the ratio here? Yeah, it's a 1-to-1 ratio. That's exactly right. So we have 1 mole of silicon dioxide gives us 1 mole of silicon carbide. So it's a 1-to-1 ratio, right? So really, this unit conversion step, we're just multiplying by 1, which doesn't do a lot, but it's important for keeping track of units, right? So we still do it just because it allows us to keep track of units to know that we're going in the right direction. To 1 mole of SiC, right? So now the moles of silicon dioxide cancels out, and we have moles of silicon carbide. Sure, that's an I, not a 1, a subscript. So now we're in units of moles of silicon carbide, which is what we want. We have one last step. And so what is that? We need the molar mass of silicon carbide, right? And what are we going to do? Are we going to multiply or divide by the molar mass? let's see, if we divide by it, we get 40.11 grams SiC per 1 mole SiC. So let's say we accidentally put this in, right? I know what happens here, or what doesn't happen. The units don't cancel, right? So as soon as we see units don't cancel, okay, we know we need to flip our ratio here, right? And that goes for any of these steps, right? If our units are canceling, we need to flip our ratio. All right, so that means that we just need to flip this. So we have 40.11 grams SiC per 1 mole SiC, right? And this is going to give us our theoretical yield. So we plug this into our calculator. 125, oops, clear. 125 times 40.11 divided by 60.08. And I get 83.5 grams of silicon carbide. And so this represents theoretically the most silicon carbide we can make from 120 grams, right? Probably when we're heating up the reaction, we're losing some other carbon and everything, which is why we don't get exactly 83.5 grams of silicon carbide, right? This was equal to our theoretical yield. And so we're asked to find the percent yield. So then how are we going to use this to find the percent yield?
Plug it in.
Yep, we're just plug it into our relationship, right? And our relationship is actual divided by theoretical, because the actual amount should be less than the theoretical maximum we can make. And then we multiply it by 100, because that just gives us a number between 0 and 1. Yep, times 100, just to get a percent. If you left it as a decimal point, you get 0.3, whatever, that's fine for me, like I don't mind, but you multiply it by 100 to actually get the percent value, right? So you plug that in, 68.4 divided by 83.4, or 83.5, depending on how you round it, times 100, you get about 82% yield, right? So this is our relationship, or our equation for our percent yield. All right, so percent yield, limiting reagent problems, these are just the exact same unit conversion problems, just with a couple extra steps added. Right, so when we move on to these problems, we just need to make sure we're comfortable with the conversions, right? And those are the hardest part, right? Actually building these unit conversion. Isn't that the actual yield? 68.4 is the actual yield that you're given, right? So the actual yield is in the original part, right? So this is one of those problems where you go through all of this work and you have to make sure you go back to get the actual value you need, right? So a lot of unit conversions is a lot of bookkeeping too, right? Keeping track of what you're doing at each step, and I know it can be hard to keep track of all the units that you're looking at. That's why, I painstakingly write every single time all of the chemical formulas for what moles and grams I'm talking about, right? Because it's important to know if I'm talking about silicon dioxide here or silicon carbide, right? So I'm always writing those units. It takes a lot longer and my hand gets sore, but I still do it, because otherwise I will be very prone to mess that up. Okay, any questions on that? Makes sense? Huh? Yeah, the unit conversion is the hardest part of this, right? The actual percent yield is, that's not that hard of a concept. But getting to that from a problem that's worded like this is where the thinking really comes in, right? Like, how do I get to what I need to? Just, this is only 2 sentences here, right? And you can think of ways, and a really good way to study is think of ways that you can modify this question, right? What if instead of just 125 grams of sand, I said, well, you have 125 grams of sand and 15 grams of graphite, which is just pure carbon, right? Then how does that change this problem? Well, now I don't get the theoretical yield right away just from converting it. I have to calculate the limiting reactant first, and then I get the theoretical yield, right? So that would be a lot more work, right? But that's one way that you can modify this problem, right? So there is a couple other examples. I might leave one up right now. The only thing I want to introduce to you guys before is that now that we have these ideas of moles, right, you're dealing with different quantities that occur in very large numbers, right? And anything per mole just means that it happens per 6.022 times 10 to the 23 times. And so we don't just have to look at grams and number of things going through chemical reactions, but we can start looking at a lot of different things too. Like, well, what if every time the reaction happens, we release a certain amount of energy? You can then use different energies as conversion factors too, right? So let's say this reaction, 137 kilocalories, and we'll go over this again on Wednesday, so you don't have to write this down, but just to prime you guys for this. Every time this reaction happens, it releases this much energy, which means that now I can get a relative amount of energy for every mole of either a reactant or a product, right? So these ratios can start be using not just for grams to grams and grams to moles, but now other physical quantities like energy. We'll start talking about pressures, concentrations, and stuff we'll also talk about on Wednesday as well. All right, so I'm going to stop lecturing there for today since I know it's been a long day, but I will leave this, let's see, which one I'll leave up. I'll leave this one up, so if you want to stay and work on this question, you're more than welcome to, but you guys are not required to stay it anymore.